In this video, we're going to talk about the exponential and logarithmic functions. So, given a number b greater than 0 and different to 1, the expression y equals to b to the x defines an exponential function with base b and domain in all the real numbers. Let's continue with some examples. If we take f of x equal 2 to the x, here the first thing to notice is that the number 2 is the base. Now this function, it's defined for all the real numbers. This means that the domain of f is the set of the real numbers. Another thing to notice is that this function is always positive. So what this is telling us is that the image of f is the set of the real numbers, but only the positive ones. To make this second property clearer, let's see what happens with f in minus 2, for example. Well, f in minus 2 is 2 to the power minus 2, which is 1 over 2 squared, so 1 over 4. F in minus 3, for example, is 2 to the minus 3, which is 1 over 2 to the 3, 1 over 8. So no matter what number we put here, we use as x, 2 to the power x will always be a positive number. And that's why the image of f is the set of the real numbers. Let's try and draw a plot for this function. And for this, we're going to be using a table of values. Here we'll write the numbers for x, and here the numbers for f of x, which equals 2 to the power x. Let's start with, for example, number 3. X equals minus 3 will give us f in minus 3, and we said here that this was 1 over 8. The same with minus 2 is 1 over 4. In minus 1, we have 2 to the power minus 1, which is 1 over 2. In 0, we'll have 2 to the power 0, and this will always give us 1. In 1, f of 1 is 2 to the power 1, which equals 2. In 2, we have 2 squared, 4. And finally, in 3 is 8. So one important thing to notice is that here f of 0 is 1, and this will happen always no matter what base we have. Also here, f in 1 will always give us as a result the base, because in general we're going to have here b to the power 0 is 1 for every b, and b to the power 1 is b for every b. So no matter what base we have, these two properties will sustain. Another thing to notice is what happens when we go in that direction. In that direction, I mean when x goes towards minus infinity. So this is when x takes big numbers but negative. Well, the function in minus 1 is 1/2. In minus 2 is 1 over 4. In minus 3 is 1 over 8. And so on. When we go towards minus infinity with x, the function f of x, or 2 to the power x, is trying to get as close as possible to 0. And remember we said that the image was the set of the positive real numbers. So it will never be negative, but it will try and be 0 as much as possible. In a similar fashion, when we go in this direction, so when x goes towards positive infinity, when we take bigger and bigger numbers of x, f of x, let's see what happens. Well, in 0 it's 1, in 1 it's 2, in 2 it's 4, in 3 it's 8, it's becoming bigger and bigger every time. So when x goes to plus infinity, f of x, or 2 to the x, is also going to infinity. So here what happens is that it seems like this is an asymptote, and we're gonna see this better when we plot the function. But this one is not an asymptote because when we go to infinity with x, we go to infinity with our function. So let's go ahead and plot the function. I'm gonna leave the plot of the function as an exercise, but I'm gonna just make a vague drawing of what the function would look like. So the information we have is that in 0, when x equals 0, the function has a value of 1. And when x equals 1, the function has a value of 2. These 2 points will not be enough to draw a function, but it is going to be enough to have a vague drawing of what the function would look like. We also know that when x goes to minus infinity, so when we go in that direction, f of x goes close to 0, so it would be something around there. And when x goes to infinity, the function also goes to infinity, so we're going to have something like up here, and that will always be growing. So with all this information we can sort of plot the function. It's going to come something like this, and it's going to be 1 here, 2, and then it's going to grow. It's going to grow exponentially. And now it's clear for us that here we have a horizontal asymptote in y equals 0. That's this line right here. This is our horizontal asymptote. But this one, well, this one is not an asymptote. Because our function is well defined for every positive number. But in this case it's not defined for 0, because if we try and find x such that f of x is 0, that is x such that 2 to the power x equals 0, x does not exist. And that's why we have the horizontal asymptote. Let's move on to view some properties of the exponentials that might be useful for us in the future. When we have a number b to the power minus n, this equals to having 1 over b to the power n. When we have b to the power r times b to the power s, this equals to having b to the power r plus s. If now we have two different numbers, a to the power r and b to the power r, then what you can do is we can write this as a times b to the power r. Similar to the second property, when we have b to the power r divided by b to the power s, we can rewrite this expression as b to the power r minus s. When we have b to the power r and this to the power s, then the exponents multiply themselves and we have b to the power r times s. And last, every time we have b to the power 0, the result will be 1. Now this last property is very important because it is telling us that the y-intercept is always 1, no matter the base. Let's move on to view some other examples. So I'm gonna have a function g of x equals 2 to the power x minus 3, and another function h of x equals 2 to the power x minus 3 minus 1. In order for us to plot these two functions, we're gonna have to remember the function f of x 2 to the x. And the reason for this is that, for example, if we do f in x minus 3, then f is 2 to the power x, so we have to change this x with x minus 3. So this would be 2 to the x minus 3, and this is exactly g of x. And in previous videos we worked with other functions of the form f evaluated in x minus h. And in this case 3 would be our number h, and h is greater than 0. So as we saw in previous videos, this is a shift towards the right. So when we try and plot g, all we have to do is shift f 3 units to the right. Let's start by plotting f. F is a function we have plotted before, so its interception is 1, and it looks something like this. Now to plot g, we have to move f 3 units to the right. So what we're gonna do is move the y-intercept. So this is 1, 2, and 3. We're gonna move this point 3 units, so that would leave it here. What I'm gonna do to make the drawing easier is draw a vertical line as if it was a new axis. Something like this. So g will pass through this point, and the y-intercept will not be 1. G will look something like this. It's an exact copy of f, only that shifted towards the right in 3 units. And now let's think about h. Well, this part of h is the same as g, so h of x is actually g of x minus 1. And if you remember from previous videos, this minus 1 is doing a vertical shift. So it's gonna move g 1 unit down. Again, the easiest thing for us to do is move this point here. So we're gonna move it 1 unit down. We know h is gonna touch this point right here. And as it's an identical copy of g, every point in g is gonna be moved 1 unit down. So what I'm gonna do is draw an imaginary line to show what would be the x-axis for h. This is not the x-axis, but it's gonna be its asymptote. So h is gonna be something like this. Something important to notice is that we knew that f had a horizontal asymptote in y equals 0. G was moved 3 units towards the right. Horizontal shifts will not move our horizontal asymptotes, so G also has a horizontal asymptote in y equals 0. But H had a vertical shift, so the asymptote, the horizontal asymptote, is gonna be moved. How many units? 1. So now the horizontal asymptote for H is gonna be in y equals -1. Now we know that the function f of x equals b to the power x is bijective for every b real number. And we know from the algebra course that every bijective function has an inverse. So now we're going to be studying logarithmic functions, and logarithmic functions are the inverses of exponentials. So now for every v greater than 1 and different to 0, the expression y equals to the logarithm base b of x defines a logarithmic function with base b and domain in all R. As before, let's start with an example. Let's work with the function f of x equals the logarithm base 2 of x. And before doing the table of values, what we're going to do is think of f of x as a number y. As we said before, the logarithmic and the exponential are inverses. So we can isolate x from this equation and have that 2 to the power y is gonna be x. And this will make it easier for us to work with the table of values. Here we're gonna have the values for x and here the values for y. And the table is gonna be the exact same as before, only that the other way around. When y equals -3, x equals 1 over 8. When y is -2, x is 1 over 4. And so on, we're gonna have the same table as before. Let's plot this function. Something important to notice is this point right here. When y equals 0 means that f of x equals 0. So when x equals 1, we have a root for our function. This is a point right here. And I'm gonna leave it to you to make the exact plot with the table of values. I'm gonna do just an approximation. The function will look something like this. It's gonna come from -infinity here, pass through this point, and then here go again to +infinity. And we can see this in the table of values. When x goes close to 0, we're taking smaller numbers, always positive. So x is going to 0. That is, we're moving in this direction. So we're going towards 0 from the right, from the positive numbers. And this is the notation. Y equal to f of x is going bigger and bigger in a negative way. So f of x is going towards -infinity. And this is exactly what's happening here. When we go close to 0, our function goes towards -infinity. Now here, when we go towards bigger and bigger numbers, so when x tends to infinity, positive, our function is also going to a positive number every time it's well defined, and it's going bigger and bigger every time, so our function f of x is also going towards plus infinity. So right now what we can say is that this is a vertical asymptote in x equals 0. And I said that this function, this is the logarithm base 2 of x, has an inverse, and the inverse is this one. So the inverse is a reflection of our function, because when we plot the exponential, it looks something like this. This point was number 1. So we can see we have a symmetry. The inverse function and the original function are reflected, and the reflection is through y equal x. So again, once we've plotted f, the logarithm base 2 of x, we can plot a function g of x equal to the logarithm base 2 of x minus 3. As before, we're going to be moving all the function 3 units to the right, because this equals f of x minus 3. So we're going to start from this point, we already know, and move 3 units to the right. So g will have its vertical asymptote here, and it's going to look something like this. And if now we try and plot another function, h of x equal to logarithm base 2 of x minus 3 minus 1, this equals to g of x minus 1, is again going to be a vertical shift 1 unit down. So this point will be here, and so will all the others move 1 unit down, resulting in a function that looks like this. So g was a horizontal shift, and it moved the vertical asymptote from x equals 0 to 2x equals 3. And the h also has a vertical asymptote in the same place as g, because vertical asymptotes are not affected when doing vertical shifts. Let's again list some properties. For this, we're going to be taking b, m, and then greater than 0, and b different to 1. The first property is that the logarithm base p of m times n is the sum of the logarithms. The logarithm base p of m over n is the logarithm base p of m minus the logarithm base p of n. The logarithm base p of n to the power k equals to k times the logarithm base p of n. This property can be used using the first one with induction. If you don't remember induction, I recommend you go back and check the Algebra 1 videos. And the final property is very useful for when we have a base we don't want to work with. So it says that the logarithm base p of any number n equals to the logarithm base a of n divided by the logarithm base a of p. And before finishing this video, I wanted to talk about a very important number. That is the number e. The number e was discovered by Euler when he was working in a very simple expression, this one. He took this expression and asked himself what happens with this expression when n grows. It's easy to notice that 1 over n will go to 0 when n is bigger and bigger. So 1 plus 1 over n will try and be as close as possible to 1. This is all when n goes towards infinity. And from this, what we can conclude is that 1 to the n equals 1. So 1 plus 1 to the over n, all this to the power n, will go to 1. Because this expression was trying to get as close as possible to 1. But this is not actually true. And to notice this, we're going to work with a table of values. On one side, we're going to write values of n, and in the other side, values of 1 plus 1 over n to the power n. When n equals 1, we have 1 plus 1 over 1 to the power 1. So this is 1 plus 1 to the power 1 is 2. When n equals to 10, I'm not going to do the calculation, you can check it with the calculator. The result of this expression is 2.594. When n equals 100, we have 2.704. When n equals 1000, this expression has a value of 2.716. When n equals 10,000, the expression values 2.7181. When it is 100,000, it is 2.7182, and so on. We can clearly see that this is not going towards 1. And what Euler did was call this value e. So what he said is that 1 plus 1 over n to the power n goes towards the number e when n goes to infinity. And the number e looks something like this. 2.718 are the first numbers. And the importance of this number is that it appears very often in nature. And that's why we're going to be working with a special function that is the exponential and the logarithmic base e. So we're going to start by plotting the function f of x equal e to the power x. And an idea to plot this function is to notice that e is a number between 2 and 3. So e to the power x will be a function between 2 to the power x and 3 to the power x. So when we plot our function, what we can do is first draw 3 to the power x. It's gonna be something like this. It's 1 in 0. And it's gonna be something like that. And the function 2 to the x is gonna be something like this. These are very vague drawings. You can check all this with a table of values or using a plotting program. So as e to the x is between these two functions, it's gonna be something like this. And if we try and plot its inverse, we're gonna have to reflect it through the yellow line, so it's gonna look something like this. and this is the logarithm base e of x, also called the natural logarithm of x. Another function that's used very often is one that looks something like this. It touches the y-axis, its y-intercept is in -1, and this one is minus e to the x. And last, one that has its y-intercept in 1 is something like this, and it also appears very often in nature, is e to the minus x. And as before, what we have here is that all these functions, 2 to the x, e to the x, 3 to the x, and minus e to the x, have a horizontal asymptote in y equals 0. Here, this function, e to the minus x, also has a horizontal asymptote in y equals 0, only that this one is to the right, and these other ones are horizontal asymptotes to the left. And as we've seen before, the logarithmic function, in this case a natural logarithm, has a vertical asymptote in x equals 0. And with this, we finish the video for exponential and logarithmic functions.